The Transient Ground Fault Test module is a simulation-based testing tool. This module can test transient ground fault and permanent ground fault relays. It has the ability to simulate the power system and to output simulated test signals from a CMC test device. In this video tutorial, we will test the directional ground fault function of a Siemens 7SA631. To do so, we will simulate a fault in the forward and the reverse directions. You can open the test module in standalone mode from the Network Simulations section in the Start page. However, we will use an OCC file in this example. The information in the global test object must be entered as a first step. In this example, the CT ratio is 60 amps to 1 amp. Regarding the global hardware configuration, either 3 or 4 voltages may be required depending on the configuration of your relay. The relay in this example uses 4 voltages measuring the residual voltage from an open delta connection. In the case that the relay uses 3 voltages, the residual voltage is calculated from the 3 phase voltages. In addition to the voltage outputs, we enable 3 current outputs to generate the ground current. As for the binary input signals, we only need the forward and reverse direction signals. When a cable type CT is used to measure the ground fault current, it is useful to perform the directional test with primary current injection. This implies that the CMC will be used as a primary test set. With this procedure, you can test not only the relay, but also the wiring of the cable type CT. For the primary current injection, we combine the current outputs from the CMC to form one test lead. The lead passes through the cable type CT several times. The more primary turns applied to the CT, the less current is required to energize the CT for testing. Counting the number of primary turns applied, we can calculate how much current must be injected from the CMC to obtain rated primary current. For example, if the CT is 60 to 1 amp rated, then, with 6 primary turns, the CMC can inject 10 amps to obtain the desired 60 amps. Once the ground fault test module is opened, remember to check that all the required signals are enabled in the local hardware configuration. The module simulates ground faults in a power system that consists of the infeed, the transformer, and the network. The network itself contains the faulty feeder, the non-faulty feeder B, and the remaining system, which includes all other non-faulty feeders. To simulate the ground fault correctly, the information about the network and the transformer is required. If you want the simulation to match a realistic scenario, it is advisable to complete all the entry fields. Otherwise, if you simply want to test the directional ground fault function, you can keep most of the settings to the default values. All the required information for the simulation is contained in the test view. In order to have a better understanding, we can have a look in detail at the settings in the single tabs. Starting with the Test tab, you can specify the type of network. Select Cable if the network is composed of underground cables or a mix between underground and overhead lines. Select Open Line Only for pure overhead line networks. Regarding the ground fault protection function, select permanent or transient depending on the setting of your relay. For instance, we will test the relay's permanent ground fault function in this example. The ground fault is always simulated at feeder A. Depending on the relay location, you can switch from a faulty to a non-faulty feeder and vice versa. In the faulty feeder A, the relay detects the fault in forward direction. In the non-faulty feeder B, the fault is detected in reverse direction. The connection of the CT star point can be set to direction line or direction bus bar. We use the connection direction line in this example. To simulate a ground fault correctly, the test module needs a value for the ground fault resistance. This is the resistance between the faulty phase and ground given in primary values. If you don't know this value, just use the default setting. The information about the transformer is contained in the next tab. In our example, the nominal operating voltages are 110 kV and 20 kV. The transformer star point can be isolated or compensated depending on the network's requirements. When compensated is selected, the fields for the detuning factor and grounding resistance are enabled. The detuning factor indicates the degree of compensation in the network. The grounding resistance is located in parallel to the Peterson coil to increase the resistive part of the ground fault current. This setting is entered as a primary value. The specifications for the rated power and impedance are contained in the nameplate of the transformer and the datasheet. The fault level at high voltage is defined as the short circuit power at the bus bar of the feeding network. Normally, the default value can be used since the resulting substitute impedance is negligible compared to the transformer impedance. The Network tab shows at first the line parameters of the faulty feeder A. These values represent the line or cable impedances between the bus bar and the fault. The settings for the positive sequence and the zero sequence are defined as primary values. Next, you can define the primary capacitive ground fault current of the remaining system, the faulty feeder, and the non-faulty feeder. The field for the CT ratio determines the CMC current outputs. For primary injection to the cable type CT, the ratio has to be set according to the number of turns. The primary entry field holds the number of turns, while the secondary entry field is set to 1. If you get the message that the ground fault currents are too high, just increase the number of turns through the cable type CT. For secondary current injection, enter the CT ratio as specified in the datasheet. Select the checkbox to use the ratio from the test object. In the last tab, you can define the start condition. If you select immediately, the test will begin as soon as you click on the Start Continue button. On binary input allows you to start the test when the selected binary input is triggered. On time trigger can be chosen when a time source signal is used to start the test. The source must be specified in the hardware configuration. Regarding the fault duration, make sure that this time is long enough to get the relay's signal. In a similar way to the other test modules, you can do automatic assessments of the binary input signals in the Time Assessments table. Just define a name and choose the start and stop conditions for the measurement. The measurement we want to take first is the time of the forward direction signal. The nominal time and deviations are required for the automatic assessment of results. The nominal time depends on the parameterization of the relay, while the tolerances are defined in the relay specifications. The Ignore Before option can be used to restrict the time measurement range. The module will ignore all signals before the start of the specified state or the selected binary transition. A second entry can be used to test the reverse signal behavior. Since we have chosen feeder A as the relay location, the fault will be detected in forward direction only. Therefore, no reverse signal is expected. In this case, only the start and stop conditions have to be defined. Doing so, we check that no reverse signal is present at the moment of the test. By starting the test, we can check the results that are collected in the time assessments table. There is no assessment for the reverse signal since we did not enter the nominal time and deviations. In the event that the relay detects a ground fault in reverse direction, you can manually assess the test as failed by means of the Manual Assessment option in the Home tab. In order to perform an additional test with the relay located in the non-faulty feeder, you can copy and paste a new module into the OCC file and choose the new relay location. The other settings in the test view stay the same. During the execution of this test, the relay should detect a fault in reverse direction. In a great number of cases, the relays are not able to determine the fault's direction when the current is too low. In this scenario, our relay is parameterized so that it outputs both the forward and the reverse direction signals. Therefore, we define both signals in the time assessment table, but only the time and deviations for the reverse direction. Once the test has been executed, we can see that the relay has issued both forward and reverse signals. Indeed, the relay has detected the ground fault. In addition to these tests, it is also advisable to check the pickup value for both the current and the residual voltage. Remember that these two tests can be performed with the ramping test module.